Today, our theme is going to be around recursion. And in recursion also, we are going to focus on problem solving using recursion. So, see, there is one thing which is common across all the problems of recursion. And what is that? Elements of choice. What is the meaning of elements of choice? So whenever you have a question where in each state or at each instant, you can take multiple decisions, you can do multiple things. There you have elements of choice. Like for example, you are given a set and somebody has asked you that generate all the subsets of this set. Now we all know in order to generate subset, what we do is for each element, we can take two actions. Either we take it or we do not take it, right? So let's say if this is your current element, you can say my first choice could be to take it and the second choice could be to not take it. Now the same thing can be done for the next element. I can say for the next element also, I can either take it or not take it. In this case also, either take it or not take it. And this is how you keep going on and on and on, right? So this was just one example where you had elements of choice. For each element, either you take or do not take. At times, the number of choices could be too many. Instead of just two choices, you could have 10, 15 different choices. So the first thing I want to tell you guys is you should learn the skill to figure out the number of choices that you have at any instant. This is a very fundamental and logical thing. It has got nothing to do with your programming skills or anything like that. It's just very logical thing, very pure thing. So I'll probably take a question and there we will try to, figure out uh, if there are some elements of choice or not. And how do we represent those choices? So let's say we have been given an integer n, for example, n is equals to 3. What we want to do is we want to print all the balanced parentheses containing n pairs of brackets. So how many of you understand the meaning of balanced parenthesis? So balanced parenthesis is something like this, right? So something like this is balanced. I mean, it's well formed. But if somebody says something of this type, is it balanced? The answer is no. This is not balanced. Why this is not balanced? Because in this case, I can say for this particular opening bracket, there is no closing bracket. So this is clearly not a balanced parenthesis. So for balanced parenthesis, the property is, the first property is of course that the number of, opening braces and the number of closing braces should be same. And second thing is for each opening brace, there should be a corresponding closing brace. For each opening brace, there should be a corresponding closing brace. You can call it symmetrical also, but this is, in essence, this is what it is. So just use your pen and paper if you want to use. And in fact, you should, because if I ask you to list down all the balanced parentheses for 3 braces, here there were only 2 braces. But if I want for 3, can you print and can you also possibly tell me that how many such varieties of braces you are able to come up with? So if you try it out, the first one and the simplest one is this. The second one could be this. The third one could be this. The fourth one could be this. And the fifth one could be this. Yeah, there are 5 of those. So guys, can you see that all these 5 set of parentheses are balanced? All these 5 are balanced. Can you see that? Yes or no? So according to the question, I'm supposed to print all of them. I don't just have to tell their count. I don't just have to tell that, hey, their count is 5. That there are 5 parentheses which are balanced and they contain three pairs of opening and closing braces. I can't say that. I have to actually go ahead and print each of them, right? So how can I go about it? What can be possibly a good way to get started? Different people come up with different logic. In fact, the moment, so yeah, a lot of you are suggesting that uh, the nature of balanced parenthesis is such that as many opening braces you have, those many closing braces you have. So let's say you have one, two, and three opening braces. That means you will have three closing braces also. That is one thing, but that is not enough. Like we saw here, that was not enough. So there are a few more properties, like many of you are saying that number of opening braces should be greater than the closing brace and all that. We'll see that in some time. But if I have to talk about the simplest solution to this, simplest, brute force, ad hoc, whatever you want to call that, what can be the way to solve it? I can probably say that, hey, if there is a balanced parenthesis containing n pairs of braces, it can be represented by a string. And how many characters will that string have? It will have 2 into n characters, right? Yeah, because n pairs means that n, these kind of n brackets will be there, and these kind of n brackets will be there, right? So three opening and three closing braces. Now, a lot of people say that, hey, for each, you have got two choices. So you can either put an opening brace or a closing brace here. Similarly, you can either put an opening brace or closing brace. So this is definitely one correct way in which you can go about it. But in this way, you will end up generating lot of parentheses which will be unbalanced and which will be completely crap, right? So for example, if you take a small value of n, let's say you take n equals to 2, you would say 1, 2, 3, and 4. I mean, every string will have four characters, two opening and two closing. Now you can say that, hey, for the first, for the first character, there are two choices. So it can either be an opening brace or it can be a closing brace. And now you can go on to the next character and you can again say there are two choices. It can either be an opening brace or it can be a closing brace. And then this process goes on. Again, for this, you would say there are two choices. It can either be an opening brace or it can be a closing brace. And again, you can say for this, there are two choices. It can either be an opening brace or it can be a closing brace. I want to tell you this thing, that the parentheses like this and this, which you have generated, are useless, right? But in this process, you will generate a lot of parentheses, which actually will be the balanced ones also. Like here, if you make the two choices, for the first choice, where you put an opening brace here, you will get something like this, which is crap. But when you put a closing brace here, you'll get this, and you're pretty happy about this. So what I'm saying is, at your base condition, at your leaf case, you will generate some crap strings. You can ignore those. And you will generate some well-formed strings. And you can ensure to only print those. You know, it is pretty easy to check whether a string is representing balanced parentheses or not. Using stack, you can do that, right? Now, you can easily figure out that all the strings which will be generated from here will be what? Can somebody tell me? All of them will be junk. All of them will be useless. Why? Because all of them are starting with a closing brace. Anything that starts with a closing brace, we know for sure is not going to be a well-formed parenthesis, is not going to be a balanced parenthesis, right? So this approach is not that great. We have to probably switch to an approach where we are only generating the balanced parenthesis. We are never ever generating something like this. Now, in order to do that, we need to observe some characteristics of balanced parenthesis. So there is one important characteristic. Let's just look at it. Yeah, maintaining opening and closing count. I mean, that's where the point goes. So let's say if you have something like this, tell me, is it balanced or not? Yes or no? This is balanced. This really is balanced if you take a look, because this one got opened over here, this one got opened over here, this one got opened over here, and this one got opened over here. So for every closing brace, there is an opening brace, right? This is important property. Like every closing brace that you have, it should have a corresponding opening brace before it. That is the most major requirement. Now, looking at here, I can say if you consider any prefix of it, let's say you are considering this prefix. In this prefix, what is the count of opening brackets? And what is the count of closing brackets? Here there are two opening brackets and one closing bracket. If you look at this particular prefix, how many opening brackets do you have? 1, 2, and 3. There are three opening brackets from here to here, right? In this part, 1, 2, and 3. There are three opening brackets and one closing bracket, right? And I mean, if you look at the entire thing, you will see that how many opening brackets are there? 1, 2, 3, 4. There are four opening brackets and four closing brackets. See, there is one very important property, and that property applies to the prefix of your balanced parenthesis. And that property says that every time the count of opening brackets will be greater than or equal to the count of closing brackets. Now, this is not a rocket science. This is a pure common sense. Why it is a common sense is because can it ever happen that number of closing brackets are more? If number of closing brackets are more, let's say if you have one more closing bracket, it means it doesn't have an opening counterpart. There is no bracket which is coupled with it as opening. So it means this is going to be a cramp. So it's guaranteed that the most important property is that while you are generating this string character by character, character by character, character by character, you have to ensure that the number of opening brackets which you have used should be greater than equal to the number of closing brackets that you have used. This is a very, very important property. How many of you understand this? Just type in yes or no. All right. Now, if you understand this, then things become very, very simple for us. Okay. Uh, so now let's look at some cases, and then things will become much more clear on the go. Let us say the value of n was equal to 3, and you are on your way to generate the balanced parentheses, which are of size 6. So let's say you put your first bracket as this, and you put your second bracket as this. And now you're wondering how many different brackets can be put over here. Can you tell me? Can you tell me how many different brackets can be placed over here? Can I put a closing brace? Just think about it. Can I put a closing brace here? The answer is no. I cannot put a closing brace. Can I put an opening brace? Yes. I can only and only put opening brace over here. So it's very important to understand that in situation where count of opening brace is equal to count of closing brace, that means our next character can only be an opening brace. Because the moment you put a closing brace here, the count of closing brace will be 2, which is greater than the count of opening brace. And we have just learned that that is not possible. That is not the characteristic of a balanced parenthesis. So this count, if it is equal to this count, your next character has to be an opening brace only. There is no other choice. Does that make sense? So this is point number 1, which you should understand. Okay, let's look at point number 2. So now again, n is equals to 3, and you are generating a balanced parenthesis of 6 characters. And so far, you have generated this. At this point of time, can you tell me how many choices do you have for this character? How many different brackets can be placed here? So here you can confidently say that, hey, my next brace over here can be a closing brace because that way it will be mapped to this. And it can also be an opening brace. Why? Because I have only used 2 opening braces and I had 3 opening braces with me. So what it points to is that if your count of opening braces is greater than, strictly greater than the count of closing brace, this situation means that there is some extra opening brace which has not been closed yet. Because it has not been closed yet, so you can definitely put a closing brace. That is definitely on your cards. A closing brace is definitely on your cards. But how about an opening brace? Can I put an opening brace also? So in this situation, you would say, yes, of course, I can put an opening brace, and you have put that up. That is the reason you are saying there are two choices, but there is one catch. Let's say you had generated something like this, 1, 2, 3, this, and now you're thinking how many different brackets can be put here. Can you tell me how many different brackets can be put here in this particular situation? Only one. And what is that? It can just be a closing brace. And why is that the case? Even though the count of opening brace is 3, which is greater than the count of closing brace, that is 1, in this case, you can only put a closing brace here. Why? Because you have used up all your opening braces. You just had 3 opening braces, right? And if you have used them all, the next one cannot be another opening brace. So I will break this thing down into two parts. The first part is 2.1, where I am saying that if the count of this is equals to count of, sorry, if the count of this is greater than the count of that, in that case, I can say if opening brackets are remaining, then I have got two choices. And case 2.2 is if opening brackets are not remaining, then there is only one choice. So if you recall this thing, it corresponds to a situation like this, where you have only used 2 opening braces and you could actually use 3 of those. So you could say that your next brace can be an opening brace also. But in this case where you have used up all the 3 opening braces, your next brace can never be an opening brace. It has to only and only be a closing brace. So now if you look at it, you have an if-else kind of condition. So your first condition is that if the number of opening brace is equal to the number of closing brace, there is only one choice. The next character has to be an opening brace. And then comes the case where number of opening braces is greater. So if the number of opening braces is greater, we check if opening braces are still remaining. Have we used them up? If we have not used them up, then our next character can be this also, and it can be that also, right? So two choices. But if we have used them all, then our next character can only be this. That's the idea. That's the basic idea. So at the beginning of the class, when I was speaking a lot about elements of choice, I spoke about it here, right? Elements of choice, find out the choices and all. This is exactly what I meant. That you look at the question and you figure out that in what situation you have what all choices. Do you understand that point? And now once you have gotten this, you can implement it pretty easily. It's not a hard problem. It's a very easy problem to implement. And very soon I'll give you a good variation of this problem, which you can think about. So guys, you know what I can say? I can say, let's say you have been given a value of n, a random value of n, let's say n is equals to 2. I can say that, okay, if you look at the diagram that I'm drawing, things will be crystal clear. So you guys tell me, what are the different variables that I need to track? I need to track the count of opening braces that I have used, and I want to track the number of closing braces that I have used. So let's do one thing. Let's start our journey with an empty string. How many opening braces are there in an empty string? 0. How many closing? 0. Okay. This case where both the counts are equal, this case corresponds to this sort of situation. So whenever the count of opening and closing are same, how many choices are there for the next character? There is only one choice. And what is that choice? It can only and only be an opening brace. So let us exercise this choice. If we exercise this choice, we would say that our next character can only be an opening brace. So let's put an opening brace and now modify these counts. What will this count be? This is the count of opening braces and this is of closing braces. So this count will become 1 and that count will remain 0. Very good. Okay, now let's look at this situation. This is the situation where count of opening brace is greater than the count of closing braces. So it corresponds to either this or this. Now you tell me, does it correspond to 2.1 or 2.2? Your count of opening brace is greater than count of closing brace. And at the same time, all the opening braces are not used up. You can see n is equals to 2 and you have only used one, exactly one opening brace. So that means you are out with two choices. The first choice is where you put another opening brace, and the second choice is where you prefer to put a closing brace. What will be the value of counts over here? 2, 0. Very good. So whenever you put an opening brace, this count increases. And whenever you put a closing brace, in that case, this count increases. So it becomes 1, 1. And then it goes on, guys. It just goes on. So now again, you tell me at this situation, here the count of opening brace is greater than the count of closing brace. So it falls either in this and or this, but you tell me whether it falls in this or that. Yeah, it falls in 2.2 because you have used up all your opening braces. So guys, if you have used up all your opening braces, like two opening braces, both of them have been used. So our next brace has to be what? Closing brace. And now the count will be 2, 1. And now at this situation, what will you do? This situation where this count is greater than that count again falls into this category where you have used up all your opening braces. So you would say there is only one choice, and that one choice is to put a closing brace. So you put it here. Now it becomes 2, 2. This is your base case. You can terminate over here. So you can say the moment you have used up n pairs of opening and n pairs of closing brace, you can just stop there and you can print the string whatever you have generated. Does it make sense? How many of you could relate to this flow that we just saw? And now the same thing you can do here also. In this side also, you can do exact same thing. Tell me, this situation corresponds to which case? Normal case, right? The first case. Where how many choices are there? There is only one choice because the number of opening and closing are same. So you can't put another closing brace because if you put that, that hasn't been opened yet, right? So there is only one choice, and that one choice is to put an opening brace, and now your count will be 2, 1. Now tell me, this thing falls in which category? It falls in this category where the count of opening is greater, but you have used up all the opening braces. If you have used up all the opening braces, there is only one choice, that now you put a closing brace, and now the count becomes 2, 2. And now again, this is your base case. So in this particular approach, what we have done is we have not generated a lot of crap, useless strings. Like we have not generated such kind of useless strings, because if you generate those, you are wasting a lot of time complexity in those, right? But if you are doing something like this, it is way, way better. It is far better than that. Trust me, it's super duper easy to code. We will quickly write some simple code of it so that you guys have enough confidence. So what I can say is, let's say there is something called as generate. There is a method called as generate. And here what you do is you pass a string. And what were the other two variables which we were passing? The count of opening braces, count 1, and count of closing braces, count 2. Okay. So, and it can be a void function. What we are doing is we are printing all the balanced parentheses containing n pairs of opening and closing braces, right? So tell me, in recursion, what is the first line of code that you write? Yes, base case. And how do you determine the base case? What is the property of base case? The property of base case is that the count of opening and closing braces are each equal to n. Very good. Very good. So we can just say that if count 1 has become n and count 2 also has become n, then I am satisfied. I will just print my string and let go, which is exit. What to do in the other cases? So now we know that there were two kinds of cases, right? Basically two kinds of cases. The first case where both the counts were equal, And second case, when the counts were different. When counts were different, there were again two cases inside that. So first we will have an if else, and inside this else, again we will have an if else. Can you visualize it the way I have said? How many of you can visualize it? So I would say that, hey, at this point of time, if count 1 is equals to count 2, that means the number of opening and closing braces are same. If the number of opening and closing braces are the same, in that case, I'll be making only one function call where I will be appending my string with an opening brace, and now this will become C1 plus 1 and that will remain C2. You understand this, right? What to do in the else case? Tell me. Else case means that count 1 is greater than count 2. So the number of opening braces is more. If the number of opening braces is more, in that case, there are two possibilities. The first possibility is that you have exhausted all your opening braces. So if you have exhausted all your opening braces, in that case, there is only one choice. So let's say if you want to write it like this, you can say if count 1 has become equal to n, if count 1 has become equal to n, what does it mean? It means that all the opening braces have been used up. If all the opening braces have been used up, there is only one choice, that you can put a closing brace and increment the count of closing brace. That's it. And what to do in the else case? In the else case, there are two choices. So you will make this call, the same line of code, and you will make this call also. So you can just copy this thing over here and you can copy that thing over here. That's it. That's really it. And you're done. Okay. So now you need to practice. You need to practice a lot of questions based on the idea of elements of choice. See, there is no backtracking over here. Why there is no backtracking? Because we are passing this string by value. We are not passing this by reference. Yeah. If you pass this by reference, in that case, you will have to backtrack and consider it as a food for thought. Just think how you would go about solving this question if you were to pass this string by reference instead of passing it by value. Just think about it. Okay, for now, we will switch the gears a bit, just a bit, because there is another important. So, in recursion, the first category is elements of choice. And then there is second category, which is very, very well known and super important. All of you would have even studied it. It is divide and conquer. How many of you have heard of it? What is divide and conquer? And can you guys quickly name at least one algorithm related to divide and conquer in your chat box? Merge sort, binary search. Yeah, you can see all of them are coming up, right? Okay, we will try to understand what is the idea behind divide and conquer. Forget about merge sort for now. Whether you know it or do not know it is none of the concern. Let us say you have an array, a simple array. Okay, and it contains some elements like 2, 1, 4, 0, 3, 6, 1, 2, something like this. And you have to find the sum of array. Okay. One way to find sum of the array is that you just write a for loop, and in order n time you can find it. You can just write a for loop I equals to 0 to n minus 1, sum plus equals to a of I, and return sum. Wow, right? Another way could be something like this, where you could say that, hey, sum of entire array can be thought of as sum of the first half plus the sum of second half. You can definitely think like this, right? There is nothing wrong in thinking like this. You can say that, hey, if I want to find the sum of an array, which is from index 0 to index n minus 1, then let's do one thing. Let's find a middle point. Let's say this is the middle point. This is mid, then this will be mid plus 1. So I can say the sum of first half can be written as the sum from 0 till mid, and the sum of second half can be written as the sum from mid plus 1 till n minus 1. Sum from mid plus 1 till n minus 1. So this is the idea. This is the idea. Now, if you remember, this is nothing but a recurrence relation, where I am saying that the sum of a large array is dependent upon the sum of two small subarrays. So you somehow find the sum of this half, let's say it is x, and you somehow find the sum of that half, let's say it is y, then your total answer will be x plus y. Do you get this expression? How many of you clearly get this expression? Right? And it works and it gives you the result. And just to make you feel much more confident about it, because after this we will solve one interesting question. So what I'm going to do is okay, let me give you the whole visualization of it so that you feel like it. With recursion, what happens is, I'll tell you one thing very honestly, and I'm sure it would happen with you. The moment you see this, it feels like it'll work, but there is something deep inside you which keeps on pinching you that how will this work? How will this work? I mean, how will the code flow and all that? Honestly, tell me, with how many of you it happens? Like you get the idea, but you are not very sure about the code. And even if you see the code, you are not sure about why that code works, how the control flows. So if you understand what I'm going to do right now, that all those doubts would be gone. So let's take a look. Let's say you have an array containing some elements. Just keep looking at the screen, and in 10 minutes, all your doubts would be gone. 1, 2, 0, 2, and let's say 3, 2, 1, 4. This is what you have. Now, in divide and conquer, what we are supposed to do is we are supposed to break this array into two halves. This is the first half, that is the second half. So we would say, let me find the sum of first half, which is 1, 2, 0, 2. And then let me find the sum of second half, which is 3, 2, 1, 4. Now, when the control comes here, you would do the same thing. You would say, let me find the sum of first half and then the sum of second half. So the sum of first half is this, and the sum of second half is this. Now again, here also you would say, let me break this into two parts. The first half and second half. The first half is this, and second half is that. Now tell me, what will you do? What will you do at this situation and this situation? When you are left over with only one element, when you are left over with an array of size 1, you can say that its sum is this element only, right? Because if somebody asks you, hey, tell me the sum of this subarray, you would say this element. Tell me the sum of this subarray. You will tell this element, right? So what you would end up doing is that from here, you will return a value 1. And from here, you will return a value 2. And now, do you remember the expression I had written? I had said, you get the sum of first half, you get the sum of second half, and you add them up. So if this value is x, this value is y, you say that your sum is x plus y. So what this function will do is, it will return 1 plus 2, which is 3. And returning so makes absolute sense. It makes hell lot of sense because the sum of this array, which is this part, is equal to 3. And that is exactly what it has returned. See, the same thing will happen here. When this gets broken down into two halves, you would return 0 from here and 2 from here. And from here, you would return 0 plus 2, which is 2, which makes absolute sense because the sum of this subarray is 2. The sum of this subarray is 2. And now what will you return from here? 3 plus 2, which is the sum of left half plus right half, and that is 5. The same thing would happen in this zone also. When this breaks down into two subarrays of size 2 each, then this further breaks down into two subarrays of size 1 each. And then this is your base condition where you return 3 from here, you return 2 from here, and from here you return 5. Thereby saying that the sum of this subarray is equal to 5. And the same thing you do here. This breaks down as 1 and 4, and you return 1 from here, 4 from here, and you return 5 from here. Finally, what you return from here is 5 plus 5, which is 10. And that makes sense because the sum of this right half is 10. So you have gotten the sum of right half. You also got the sum of left half. So your entire sum is 10 plus 15. So this function would return 10 plus 5, which is 15. And that would be your answer. So did you realize that how the recursive call flow happened. You went from top till the bottom, and then the values got returned, and then you accumulated those values and returned. Then again, the control went here, you returned something, you accumulated them, returned. So it's like the return happens from bottom to top. And whenever you accumulate the values, you sum them and then you return to your parent. Like if you look at this, whenever it got the sum of left half, right half, it accumulated it and returned it. So there are two parts: divide, where you divide the problem into two halves. And when you have solved them, you conquer. Conquer means you add them and return the result. So this is classical divide and conquer. Does it give you much more confidence in believing that this really works? And yes, this really works. One of you asked this question, that isn't it better to iterate? It's not about better or something. It's about learning a new paradigm, because there are so many situations where you will have to use approaches like these. Okay. And as you move ahead, you will find plenty of examples. I mean, there's just no dearth of examples. Okay. How do you implement this? You would say, let there be a function sum. And here, what can I pass? I can just pass the starting and ending index of my entire array. So let's say I'm passing I comma j, I and j both are integers. And now my logic will be pretty simple. First of all, tell me what will be my base case. The base case will be whenever I have a subarray of size 1. In a subarray of size 1, the starting index and ending index will be the same, right? Yeah, that is the property. See, like when you pass this array, what do you pass? You pass the starting index 0, you pass the ending index 7. I'm just writing 0, 7. And then you find the midpoint. Midpoint is 3. So now you pass 0 to 3. And you can see this array is nothing, but it is subarray from index 0 to index 3, right? And then you find the midpoint again. It is 1. So your left call is from 0 to 1 and the right call is from 2 to 3. Now again, you find the midpoint here, and then your left call is from 0 to 0, and the right call is from 1 to 1. So whenever your I and j are equal, it means you're talking about a subarray of size 1. Is that clear? Did you get this point? So if I and j are equal, then the sum will just be that element, which is a of I. Otherwise, what we do is we find the midpoint, I plus j divided by 2, and then we say, let's find the sum of left half, which is from I to m. Let's call it x, and find the sum of right half, which is from m plus 1 to j, and then return x plus y. That's it. This is the code for whatever I have spoken so far. Does it make sense? How many of you can connect to this code? Now, what is the time complexity of this code? Okay, so one answer that I'm getting is log of n. In fact, two people are saying log of n. How many of you support log of n? Okay, there are some. So let me tell you one thing. If this approach would be actually taking log of n time, then the entire world, while finding the sum of array, would be using this approach only. But do you use this approach? No, you don't use this approach. You write that simple for loop. And tell me one more thing, use your common sense. If I give you some coins, if I give you some coins and I ask you to find their sum, can you find the sum of all the coins without looking at every coin exactly once? If you want to find their sum, you have to look at every coin at least one time. So if you have to find the sum of n elements, you have to look at each element at least one time, right? If you are saying you're only doing log n operations, that means you're not even accessing all the n elements. How can you find this sum without accessing all the elements? You have not done any pre-computation also. So it is guaranteed that no matter where the world goes, the time complexity of finding sum of an array can never be smaller than order n. Can never be smaller than order n. Now, to discuss what is the time complexity of this approach, let us understand. So just tell me how many function calls are there in the last level. Number of function calls. The number of function calls in the last level, if you take a look, is n. Because this function call is from 0 to 0, this is 1 to 1, this is 2 to 2, indices, right? Above it, how many function calls? How many function calls are there over here? N by 2. And above that, N by 4. And it goes on and on. And at the top, there is only one function call, right? N by 4, so on till 1. Now, if I sum this thing up, if I'm just trying to find out that what is the total number of function calls, I would say it comes out to be n plus n by 2 plus n by 4 plus n by 8, so on till 1. If you take n common, you get 1 plus half plus 1. Have you seen this series somewhere? How does this series look like? Yes, it is a geometric progression. Now, can you tell me what will be the sum of this series? One interesting thing about this series is that here the common ratio is smaller than 1. The common ratio is half. So every next term is smaller than the previous term. Half is smaller than 1. 1/4 is smaller than half. 1/8 is smaller than 1 by 4, right? So no, you don't need to estimate anything. Just use the GP formula. Even if there are infinite terms in the worst case, do you remember the sum of infinite GP? What is the sum of infinite GP? It is A upon 1 minus R, where A is the first term, 1. 1 minus R, common ratio is half. So this value is 2. Very interesting. So this thing will never be greater than 2. In fact, it will never be equal to 2 also, because it will be equal to 2 when there are infinite terms. And infinite is just a theoretical concept. It is not a practical possibility, right? But anyways, the maximum value of this expression is 2n. In fact, it will not be 2n, it is approximately 2n. It will always be smaller than or equal to 2n, right? See, you count the number of function calls. Let's count the exact number of function calls in this case. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So how many function calls are there? 15. And how many elements were there in the array? 8. Right? This 15 is exactly equal to 2 into 8 minus 1, right? And that is reflected in what we just understood over here, right? So that basically means that the sum of this series is never equal to or more than 2 into n. So yeah, 2 into n, you can ignore 2 and you can say that the complexity is around order of n only. So this was one very, very important approach uh, related to divide and conquer. Okay. All right. All right. Now, there is one very famous question. We'll take that up. That question says something like this. It says that you have an array, okay, in which there are some elements, let's say 2, minus 1, and then you have 3, 6, minus 7, something like this. And you have to find the maximum sum subarray. You understand what is subarray? Subarray means array inside an array. So it has to be contiguous. So can you tell me which subarray has the maximum sum, and what is that sum? Yeah, I was quite sure I would hear about these algorithms like Kedane and all. Yeah, we'll talk about it. We'll probably touch upon it. But what is the answer for this array? Yeah, so I think maybe you can take this part, right? What is the sum of this part? 10. Somebody is getting 11. Can you get 11? Is there a way you can get 11? I don't think you'll be able to get 11 in any way, right? So the maximum that you can get is 10. So the answer over here is 10. Cadence is an algorithm which solves this problem in order and time. People learn about Cadence after learning Cadence. I mean, they are not, maximum people are not able to come up with Cadence algorithm on their own. We will not even touch this algorithm because we have learned divide and conquer. So we will try to apply that if at all, right? Now, here What could be the brute force way? Forget about using Cadane, optimizing it. Let's say if you have to solve this question using a simple brute force approach, how can you go about it? So yeah, two for loops, very good. You can write nested for loops. You can consider, so you can write for I equals to 0 to n minus 1. And for j equals to I to n minus 1. So basically what you're doing is you're fixing your starting index I. And if your starting index is this, then your ending index can be anything from here till the end. So let's say if your ending index is j, then you would find the sum of this subarray. So basically here you will consider the sum of all the subarrays, and whichever has the maximum sum, you would return that. This is going to take order n square time. Okay, look, even if you use prefix sum approach, then in the after finding the prefix sum, you would want to write this for loop, these two for loops. And then inside this, you would say that, okay, the sum from I to j can be found using that prefix formula, right? So the complexity would still, end up hitting order n square. Now, why this approach is a waste and how can it be optimized? Let me just tell you that. The divide and conquer approach to this is very, very clever. Okay. So let me just explain what happens in this approach. In this approach, what you do is, let's say you have an array. Okay. And this is your index I. And you have fixed this as your starting index in your ith iteration, let's say. Let's say this value I is equals to 4. Now what you do is that you consider this subarray, then you consider this subarray, then this subarray, then this subarray, sorry, the next one, and then the final one. Think of it in this manner. Let's say there was an index over here, which was index 7, right? So you would have considered this subarray, and then you would have considered that subarray, and then that, and then that. So you would end up considering so many subarrays, so many subarrays that are crossing index 7, that are crossing index 7. See, this is also crossing index, and crossing means either touching or crossing and going ahead. So this was the first one, this was the second one. So there are so many of them. Divide and conquer approach says the reverse of it. It says something like this. It says that, hey, think of it in this manner, that if I have an array, and let's say the middle point of this array is 6, right? Then whatever is my answer, whatever is my maximum subarray, either it would be passing through 6, maybe start. I mean, 6 would definitely be a part of it. And then because it's a subarray, so either it would continuously go in this direction and some part of it might go in that direction. So either it would be a subarray which crosses through this element, or it would be a subarray which is completely contained inside this, or it would be a subarray which is completely contained inside it. Are you able to understand this point that I'm saying? It could be a little tricky for those of you who are learning it for the first time. But yeah, so the idea is that whatever is your answer, whatever is your maximum sum subarray, that maximum sum subarray would either be passing through this index, passing through this element, or it would be completely contained inside this, or it would be completely contained inside this. So just think of it in this manner. Let's take some examples. Let's say you had 6, minus 1, 5, minus 10, 2, minus 3, minus 1. What is your answer here? So in this case, I believe your answer is this, right? Yeah, this is your answer. Here, this was your middle point. And here, whatever was your answer was crossing through this, was crossing through 6, right? And you found out that this one had the largest sum, and that sum was how much? 12. And you said that, yeah, your answer is 12, and then your job is done. But what I'm saying is that this is one possibility, that your answer passes through middle. But there are two more possibilities. Those two possibilities are that either your answer is completely contained in this block or your answer is completely contained in this block. And I can show you examples. I can show you examples. So let's say you had something like maybe -5 and then you had 6 and then -2, 9, and then you had something like 1, 0, 4. In this case, what is the answer? Tell me. Yeah, in this case, you can see this is your answer, right? This is your answer. So this is completely contained inside this part. Now, I'm not saying that this part itself will be your answer. I'm not saying that at all, because it could very well happen that maybe you had something like -10 over here. So this entire part is not your answer, but whatever is your answer is completely contained inside this part. And now just think logically. For every yes, there is a no. For every yes, there is a no, right? So if somebody is saying that, hey, my answer definitely crosses, okay, my answer definitely crosses through midpoint. This is one possibility. This is one possibility. What is the reverse of this possibility? The reverse of this possibility is that my answer definitely doesn't cross mid. So if your answer crosses through midpoint, then in that case, your answer could either be this, or it could 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 be this entire thing, right? So that all falls in this category. But when you say your answer definitely does not cross through mid, what does it mean? It means that either your answer is completely contained in this part or contained in this part. Now, how many of you can understand this logic? Just type in yes or no. If you got this idea, then this is the sort of thinking which is really required in framing your own divide and conquer solutions. So now what I can do, I can say that, okay, all right. Let's say there is an array. There is an array. It has a midpoint. At midpoint, there is an element, let's say 4. I would say that my answer is equals to 4. If I am considering the case where my answer definitely crosses through mid, I would initialize my answer to 4. And then what I'll do is, let's say this side you had 5, and then -6, and then 9, and then -2. So what I'll do is that now I'll check 4 plus 5 is 9. So I'll say that, yeah, 9 included, this element included. 9 plus -6 is 3. So I would not want to include this, right? But I know that now the sum has become equal to 3. 9 minus 6 is 3. 3 plus 9 is 12. So that's great. That's great. This much of sum is becoming 12. So now I would want to update this to 12. Now, this much of sum 12 plus -2 is becoming 10, which is smaller than this, so I would not update it. So I would stop till here. I would say that the best possible sum which crosses this and goes in this direction is 12. And now the same thing can be done in this reverse direction also. So let's say you had, now currently your answer is is 12. Now let's say you had a value over here, -1, right? You would say that, hey, 12 minus 1 is 11. So I would not update. But the sum is 11, right? The sum is 11, given that you just got this element over here. And now after that, let's say you had 7. So now it becomes 18. The moment it becomes 18, you would be like, okay, let's include it. The moment you include it, this sum becomes that much. And now let's say after that you had maybe -2 and then maybe -3 or whatever. So basically in this process, what happened, you found out that, hey, the best possible sum which crosses this is equal to how much? Is equal to 18, right? And you can do this thing in order n time. You can do this thing in order n time. You just need to initialize your sum to this variable. And then you can have a current variable which is equal to sum. And you just go right, keep on adding the elements. And if you get a value of current which is greater, just update. And do the same thing in left side also. So whatever would be your final answer, that would be the best possible sum that you would get if your subarray is crossing this point. And now there are two possibilities left. First possibility is that your answer is either contained in the left half or it is contained in the right half. So you would make a call for the left half, make a call for the right half, and then out of all the three options, whatever is the best answer, that would be your actual answer. So imagine that the best possible answer from here is answer left. And the best possible answer from here is answer right. And the best possible answer that crosses the midpoint is answer mid. Out of these three, whatever is the maximum, that would be your answer, your overall answer. This is a little hard for certain people to understand, but still, I'm just curious to know how many of you got it, how many of you understood it. So do you want to see the code of this? And then this is for the right half, maximum answer from the right half, answer right. And now whatever I'm doing here, I'm doing that to find out that what is the maximum answer where my subarray crosses the middle element, which is nums of m. So I initialize it to this, and this while loop traverses the right side, and this while loop traverses the left side. And finally, I have these three things, and whatever is the maximum of these three things, that is our final answer.